We will learn two theorems. First, the perpendicular axis theorem, and then the parallel axis theorem. In perpendicular axis theorem, we will consider a two-dimensional mass distribution, and there is a z-axis, and the mass distribution is rotating about the z-axis. Then we take a small mass dm at point P, and then we join the origin with the point. Then we call that position vector r. So OP vector is the r vector. Now the moment of inertia I about the z-axis is equal to dm mod r square, or we can write Iz equal to integral dm r dot r. We know that r is ix plus jy, then r dot r is x square plus y square. Then we get Iz equal to integral dm x square plus y square, or we can write Iz equal to integral dm x square plus integral dm y square. This is the perpendicular distance from y-axis, and this is perpendicular distance from x-axis. Then we can write Iz equal to Iy plus Ix. So this is the perpendicular axis theorem that we have considered a two-dimensional mass distribution. Before we go to the parallel axis theorem, let us draw a picture of a three-dimensional mass distribution, and there is a origin O, and the axis is passing through this origin. The mass distribution is rotating about this axis. Now if we consider a small mass at point P, then and join origin with that point P, then OP we call the position vector. And now let us take a unit vector along the axis. Let us call this axis A. So n is a unit vector along axis A. Now what is the distance between the point and the axis? Let us call this point as C. Then what is Cp? Magnitude of Cp is r, magnitude of r sine theta, where theta is this angle, theta. Then we can say that Cp equal to magnitude of r cross n. So to prove perpendicular axis theorem, again let us consider a three-dimensional mass distribution, and there is an axis axis A, this is passing through the origin. And then there is a second axis which passes through the centroid. Second axis B is passing through the centroid. Again, I take a small mass distribution Dm at point P, then draw the unit vectors. Unit vector n along the axis A, and axis B is parallel to axis A. So the unit vector along the axis B is again n. Now let us join O with P. Then we call it R. Then join C with P. Then we call R dash and join O with C. Then we call it R. So from triangle law, we get R equal to capital R plus R dash. Now let us start with IA, moment of inertia, when it is rotating about axis A. So IA is integral dm r cross n magnitude square. Now IA is integral dm magnitude of r plus r dash cross n square. R cross n square plus integral dm r dash cross n square plus there is a cross term 2 integral r cross n dot r dash cross n dm. Okay, so this is a constant. This is d square. What is d? And we call OD magnitude. We define this as d. This is the perpendicular distance between axis A and axis B. IB is integral dm r dash cross n whole square. So we get integral d square integral dm plus this is IB, and then here let us rewrite 2 r cross n, this is a constant, goes out of the integration, dot r dash cross n dm. Then we can write IA equal to IB plus MD square plus 2 R cross N dot integral R dash cross N dm. Now IA equal to IB plus MD square plus 2 R cross N dot, you can write integral r dash dm cross m. But from the property of centroid, this is 0. Vanish from the property of centroid. And finally we get IA equal to IB plus MD square. So this theorem says that suppose we know the moment of inertia about an axis passing through the centroid. We call it IB. And we know the total mass and we know the distance of another axis which is parallel to the first axis. The second axis is called axis A. Then IA equal to IB plus MD square. And I have taken this proof from the book of H. Goldstein. So I hope that this discussion will be useful for you, and thank you for watching.